So this is week 12 of applied thermodynamics course. So we were looking at compressible flows. So we calculated the stagnation properties and how the flow occurs and the normal shocks and what normal shocks when the process occurs the normal shock. So what how the properties changes across a normal shock, and those were looked at in the previous week. In this week, what we'll see is flow through a nozzle. So the compressible flow. So when you have a convergent nozzle, if you're having a flow, and can be shown that when flow occurs in a converging nozzle, so your area decreases, and they decrease in area, your velocity increases, and at a certain area ratio you will get a maximum possible mass flow rate. It's a choke flow, or when you are having reaching Mach of 1, speed of sound. And if then to attain supersonic speed, when you are having converging nozzle for with the inlet being supersonic, then in that case a deceleration happen and you'll have a lower Mach number at the exit. Similarly, for attaining a convergent supersonic speed from subsonic this thing, you use a convergent divergent nozzle. So in a converging section, your subsonic fluid accelerates and reaches sonic at throat in a converging section, and if a converging section is used for a supersonic, then it decelerates. And similarly, in a diverging section, the supersonic accelerates and the Mach number increases at the exit, and similarly your subsonic will have decelerate and it will reduce Mach number at the exit. So if you see in a converging diverging section, now you can have two. So you can have a diverging and then converging, so having a maximum area at the mid, and I can have a minimum area. So the only possible way of having at throat Mach 1 is having a minimum area. So if you're using a maximum area, if you're using subsonic at the inlet, so it reduces and your Mach number is lower compared to inlet when you are having a higher area. And similarly, if you are having a supersonic speed at the inlet to the diverging section, then again your Mach number is more, so you will not get a sonic velocity at the throat or Mach at 1. So you should have a converging diverging section in that case. So we'll see similar problems then calculate how the process is when a flow is occurring through these nozzles, and also some steam nozzles. So other cases, when you are having a nozzle, so you are having a Mach when your exit pressure is lower at certain lower than certain value, you may experience shock at after the throat, because your exit pressure is lower, and then this may be reducing it further. This shock will shift from this diverging section, and it can have a section at the exit of the nozzle diverging section, and then reducing it further you have your normal shock happening at outside your nozzle. So those are the cases, and the flow can happen, can increase the flow based on either you increase the initial stagnation pressure or exit pressure being reduced. So those are the cases where you can increase your flow. So with that, we'll move into seeing some problems in flow across the nozzle. So the first one is a nozzle is designed assuming a reversible adiabatic flow with an exit Mach number of 2.8 while flowing air with a stagnation pressure and temperature of 2 megapascal and 150 degrees Celsius respectively. The mass flow rate is 5 kg per second and the gamma may be assumed to be 1.4 and constant. So determine the exit pressure, temperature, exit area and the throat area. So what is given is, we know the exit Mach number, and the stagnation pressure and temperature is known, and also the mass flow rate. So we need to find out what is the exit pressure, temperature and exit area, and also the throat area. So we'll see how to solve this. Since the exit Mach number is 2.8, so we are using a converging diverging nozzle in this case. So we'll get 2.8 at the exit. So and we'll have a choke flow such that you have at throat you have Mach number of 1. So in that case, the mass flow rate can be written expressed as this. So m dot by A star as a throat area equals P naught times root of K by RT or gamma by RT into K plus 1 by 2 in raised to power minus K plus 1 divided by 2K minus 1. So your mass flow rate by area is, now we know the stagnation pressure, we know the stagnation temperature, and we also know that gamma is 1.4 and it is a constant for the process. So the stagnation pressure is 2 megapascal and stagnation temperature is 150 degrees Celsius. So 2 megapascal to convert into kilopascal, 2000 into 1000 Newton per meter square into root of 1.4, which is the gamma value, divided by 0.287 into 423.15 times 1000 to convert R into joules, multiplied by 1.2 raised to power minus 2.4 by 0.8. So this gives you the mass flow rate by area is 3929.72. Since we know the mass flow rate, so the mass flow rate will be constant. So at the throat area also your mass flow rate is 5 kg per second. So area at throat is m dot by 3929.72. So m dot is 5. So you get area of the throat is 1.272 into 10 power minus 3 meter square. So from table now we can find out what is the, since we know the pressure and stagnation pressure and stagnation temperature, and we also know the exit Mach number, so we can directly estimate your exit temperature and exit pressure. So for that we'll use the chart. So for this we'll use mass as 2.8, Mach number is 2.8. This is the exit Mach number. For the isentropic flow chart 2.8, you get T by T naught is 0.3894 and P by P naught is 0.0368. So that's what is written here. So you have we can find out the exit temperature and exit pressure using the chart or using the table, and then your area, exit area is A star into AE by A star. So that value can also be obtained from chart. So if you see, A by A star is 3.5 So we know the area ratio from the table for 2.8. So AE equals A star into the ratio, which is 3.5. So we get the exit area as 4.452 into 10 power minus 3 meter square. And similarly, we can find out the exit temperature. So exit temperature is 0.38941 times your stagnation temperature, which is 423.15. So that gives you exit temperature as 164.8 Kelvin. And similarly, your exit pressure is 2 megapascal. So 2 into 10 power 6 into 0.036848. So that comes out to be 73.7 kilopascal. So next question is, a converging diverging nozzle operates at steady state. Air as an ideal gas with K equals 1.4 enters the nozzle at 500 Kelvin 6 bar and a Mach number of 0.3. A normal shock stands in the diverging section at a location where the Mach number is 1.4. The cross-sectional areas of the throat and the exit plane are 4 cm square and 6 cm square respectively. The flow is isentropic except where the shock stands. Determine the exit pressure in bar and the mass flow rate in kg per second. So what is given is, we have a converging diverging nozzle as shown in the figure here. So the inlet conditions are specified. So it is in Mach number 0.3, the subsonic flow 6 bar and 500 Kelvin, and the throat section is 4 cm square, and your exit is at 6 cm square. So your throat at the diverging section, you are having a normal shock wave, and that is occurring at Mach number of 1.4. So we need to find out what will be the exit pressure such that your shock is at the location where your Mach number is 1.4, and also find out the mass flow rate corresponding it. So we know exit area by area of the throat is can write AE by AX into AX by AY, and AE by AY can be written as AE by X into P naught Y by P naught X. So to determine, first is to determine the stagnation pressure for Mach number of 0.3. So from the isentropic chart we can find out the ratio corresponding to Mach number of 0.3, and since we know the inlet pressure, you can directly find out the stagnation property. So for Mach number of 0.3, the ratio is 0.9395. So P naught at the state 1 is 6 by 0.93947, which gives you 6.39 bar. So now, since we know that the flow is isentropic, so till P naught at X, your stagnation pressure will remain same, because across the normal shock there will be reduction in the stagnation pressure and your entropy increases, and this all we saw in the previous week. So up to location X, your stagnation pressure will remain same, so 6.39 bar, and we know that your Mach number at 1.4, your normal shock is occurring. So from the shock table, at 1.4 bar, we know that the pressure ratio is 0.9582 for the stagnation pressures. So 0.9582 at the exit of shock to the inlet of the shock. So from there we know AE by AY is 6 by 4 the area ratio into 0.95819. So this gives you 1.4373. So from now we know the exit area to the throat area. This is 1.4373, and since somewhere around 0.45461. So for the area ratio of 1.4373 from the table, go across A by A star, we get somewhere between 0.46 and 0.44, so close to 0.46 so the Mach number comes out to be 0.461 interpolating, and the corresponding P exit by stagnation pressure is close to 0.8650, or so it comes out to 0.86351. So we know the exit pressure ratio, and we need to find out the stagnation pressure at P naught y, the exit of the normal shock. So that will be same as your exit stagnation pressure. So P naught y by P naught x is we have already found out, which is 0.95819. So P naught y will be we have found out the stagnation pressure at the inlet to the normal shock, which is 6.39 into 0.95819 gives you 6.12 bar. So solving for the exit pressure, P is P naught E equals 0.86351. So the exit pressure will be 6.12 into 0.86351, which gives you 5.28 bar. Next is we have found out the exit pressure for which your normal shock occurs at 1.4 Mach number. Now we need to find out the mass flow rate. So mass flow rate is rho AAB, or AAB into divided by specific volume. So at Mach number of 0.3, your area ratio is area at the inlet to the throat area is from the table. So Mach 0.3 is 2.0351. So area at the inlet is 2.0351 into 4 centimeter square, which is the throat area. So it gives you area as 8.1404 centimeter square, which is the area at the inlet. So now we need to find out the specific volume. So assuming an ideal gas equation, V is specific volume is RT by P. So R is 8.314 divided by 28.97 into your temperature is 500 Kelvin, which is given, and pressure is 6 bar. So converting R into joules, so multiplying by 1000 and dividing by 10 power 5 to convert it into pascals. So we get specific volume as 0.2392 meter cube per kg. So finally Mach number is V by your speed of sound, which is the root of gamma t. So we can find out volume velocity. So velocity here is Mach number into root of gamma t. So Mach is 0.3, and then gamma is 1.4, and similarly R is 8.8314 divided by 28.97 into 500. So this gives you velocity as 134.5 meters per second. Next we can find out the mass flow rate. So mass flow rate will be rho AV. So A is we have found out 8.1404 multiplied by volume, which is 134.5, divided by a specific volume, which is 0.2392. So this comes out to be converting area into meter square. So this comes out to be 0.4675 kg per second. So that is the mass flow rate through the nozzle. So next is it possible to accelerate a gas to a supersonic velocity in a converging nozzle? Explain. So no, it is not possible. So the only way it can be done is having a converging nozzle and then a diverging nozzle. So if you see, this is governed by this equation. So if your Mach number increases, is greater than 1, so this is 1 minus m square becomes negative, so this total quantity will become negative. So your velocity will only increase, the dV will be positive only when dA is positive. So the area should increase, then only your volume will increase. So having a converging nozzle will not give you a supersonic velocity, but if your dA is reduced, so V will reduce and it will decelerate and it will go to subsonic when you are having and then similarly, if your Mach number is 1, this whole quantity on the right will be negative, so minus dV. So if your velocity is increasing, so area should reduce. So the only way to have a supersonic velocity is having a converging nozzle and then followed by a diverging nozzle. Next is helium enters a converging diverging nozzle at 0.7 megapascal, 800 Kelvin and 100 meters per second. So what are the lowest temperature and pressure that can be obtained at the throat of the nozzle? So we are having a converging diverging nozzle and it is entering at 0.7 megapascal, which is 7 bar, and 800 Kelvin, and velocity is 100 meters per second. So what is the lowest temperature and pressure that can be obtained at the throat of the nozzle? So see, the lowest temperature and pressure that can be obtained at the throat are the critical temperature T star and critical pressure P star. So for that we need to first determine the stagnation temperature at the inlet T0 and P0. So T0 is T plus V square by 2 Cp. So here we cannot use the isentropic flow table because that is defined for gamma of 1.4. So here, since we are using helium, so we have to go to the equations to find out the stagnation temperature. So this we are getting it from the energy balance and assuming Cp is constant. So T0 equals T plus V square by 2 Cp, so which gives you 800 plus your velocity is 100 meters per second square. So 100 square divided by 2 into 5.1926 kilojoule per kg. This for helium. So this gives you 801 Kelvin is the stagnation temperature, and similarly stagnation pressure P0 is P into T0 by T raised to power gamma by gamma minus 1, because we are assuming that your stagnation temperature is when you are isentropically bringing it to the velocity to 0. So that's why you can use isentropic compression equation. So P0 is P into T0 by T raised to power gamma by gamma minus 1. So P0 is 0.7 megapascal and T0 we have found out 801, and your inlet temperature is 800. So and gamma for helium is 1.667. So this gives you P0 as 0.702 megapascal. Since for an throat section, T star is defined as T naught by 2 by K plus 1 or gamma plus 1. So T naught is 801 and 2 divided by gamma is 1.667 plus 1 gives you T star as 601, and P star will be similarly P naught multiplied by 2 into gamma plus 1 raised to power gamma by gamma minus 1. So this is the same as this expression. So this comes out to be 0.702 into 2 by 1.667 plus 1 raised to power gamma by gamma minus 1. So this comes out to be 0.342 megapascal. So this is the minimum temperature and pressure that can be obtained when Mach number is 1. So moving on to the next question. Calculate the critical temperature, pressure and density of air at 200 kilopascal, 100 degrees Celsius and 250 meters per second, and B, helium at 200 kilopascal, 40 degrees Celsius and 300 meters per second. So first is air. So 1.4 we can use the chart table as well. So what we need to find out is the critical temperature and pressure and density when it is air. It is entering at 200 kilopascal, 100 degrees Celsius and 250 meters per second. And similarly for helium, which is coming at 200 kilopascal, 40 degrees Celsius and 300 meters per second. So the values are given. Properties for air: R is 0.287 and gamma is 1.4 and Cp is 1.005 kilojoule per kg Kelvin. Similarly for helium, your R is 2.0769 gas constant kilojoule per kg Kelvin, and gamma is 1.667, and your specific heat is 5.1926 kilojoule per kg Kelvin. So these are all given. So to find out the critical temperature and pressure, so we need to first find out the stagnation properties. So first T naught. So we know the inlet coming temperature is 100 degrees Celsius. So T plus V square by 2 Cp. So T is 100, V is 250. So 250 square divided by 2 into Cp is 1.005 for air. Converting kilojoule into joule. So we get 131.1 degrees Celsius. And similarly P naught is P times T naught by T raised to power gamma by gamma minus 1. So it comes out to be 200 into 404.3 divided by 373.2 raised to power 1.4 divided by 1.4 minus 1. So it comes out to be 264.7 kilopascal. And rho naught is P naught by R T naught. To 64.7 is the P naught. R is 0.287 for air, and T naught which we have found out is 404.3 Kelvin. So the rho naught comes out to be 2.281 kg per meter cube. So now we are using the same expression for finding out the critical temperature. T star is T naught into gamma 2 by gamma plus 1. So T naught is 404.3 and 2 divided by 1.4 plus 1 comes out to be 337 Kelvin is the critical temperature for air. And similarly for P star is P naught into T naught by T raised to power gamma by gamma minus 1. And since we know here T star by T, so it's 2 pi k gamma plus 1. So P star becomes P star equals P naught into 2 by k plus 1 raised to power k by k minus 1. P naught is here, which I found out 264.7 kilopascal. So substituting that and gamma value, we get P star as 140 kilopascal. So next is to find out the critical density. So similarly again same, assuming the isentropic process between the two, we get rho by T raised to power gamma minus 1. So we get rho star is rho naught into T star by T raised to power 1 by gamma minus 1. So this comes out to be rho naught into 2 by k plus 1 raised to power 1 by k minus 1. So rho naught is 2.281, which we have found out, into 2 by 2.4 raised to power 1 by 0.4, comes out to be 1.45 kg per meter cube. So same process we do it for helium. So again, helium is T naught is T plus V square by 2 Cp, and T is 40 degrees Celsius and V is 300 meters per second. So T naught comes out to be 131.1 degrees Celsius, and similarly P naught is P into 2 T naught by T raised to power gamma by gamma minus 1. P is 200 kilopascal, and temperature we have found out T naught 404.3. Sorry, this comes out with 48.7 degrees Celsius, and V is 300 meter per second square. So T naught is 48.7. So P naught becomes 200 into your T naught value, which is 321.9, and T is 40 degrees Celsius, so 313.2 Kelvin raised to power gamma by gamma minus 1. So P naught comes out to be 214.2 kilopascal. And now rho naught is P naught by R T naught. Substituting the P naught and T naught value, we get rho naught as 0.320 kg per meter cube. And similarly, using the critical ratio formula, T star is T naught into 2 by gamma plus 1. T star comes out to be 241 Kelvin, and P star comes out to be 97.4 kilopascal. And then rho star density is 0.320 into 2 by 2.67 raised to power 1 by 0.667, gives you 0.208 kg per meter cube. So the other way of solving this is, the first part we can directly use the table here and then find out the values. Can first find out the gamma RT value to find out Mach number, and then use the table directly to find out the ratio, area ratio. So air at 200 kilopascal is 100 degrees Celsius, and Mach number of 0.8 flows through a duct. So calculate the velocity and the stagnation pressure, temperature and density of the air. So what is known is, through a duct you have pressure is known 200 kilopascal, temperature is known 100 degrees Celsius, and Mach number is given as 0.8. So let's see how to solve this. So first we'll find out velocity. So to find out velocity, we need to find out the speed of sound. So C is root of gamma RT. So gamma is 1.4, R is 0.287 for air, and T is 373.2. Given is 100 degrees Celsius, so 373.2 into 1000 to convert R into joules. So it comes out to be 387.2 meters per second. Next is the velocity is Mach number times the speed of sound. Since the inlet Mach is at 0.8 and speed of sound is 387.2, So the velocity comes out to be 0.8 into 387.2 is 310 meters per second. And since we need to find out the density of air, so rho is stagnation density of air. So first we'll find out the density. So rho is P by RT. So pressure is 200 kilopascal, R is 287, and then T is 373.2. Converting P into Pascal, so multiply by 1000, so we get 1.867 kg per meter cube. So that is the density at the inlet. So now we need to find out the stagnation property. So stagnation property in terms of Mach number is given as T naught is T times 1 plus gamma minus 1 into Mach square divided by 2. So your temperature is 373.2 multiplied by 1 plus 0.4 into 0.8 square divided by 2. It comes out to be 421 Kelvin. Then P naught becomes P naught is P times T naught by T raised to power gamma by gamma minus 1. So P is 200 kilopascal and T naught is 421 divided by 373 raised to power 1.4 by 0.4. It comes out to be 305 kilopascal. And similarly your stagnation density is rho times T naught by T raised to power 1 by gamma minus 1. So rho is 1.867 multiplied by the ratio 421 by 373 raised to power 1 by 1.4, which comes out to be 2.52 kg per meter cube. So the only ratio is required is T naught by T, so we can find out the rest assuming an isentropic condition between isentropic compression between the 2 points, the stagnation and the inlet temperature and pressure. So here the same formula, if you assume Mach number as 1, so it becomes K plus 1 by 2, so which is what we used previously to find out the critical ratio. So it's the generalized formula. So T naught is T times 1 plus gamma minus 1 into Mach square by 2. The next question is, an ideal gas with gamma of 1.4 is flowing through a nozzle such that the Mach number is 1.8 where the flow area is 36 centimeter square. Approximating the flow as isentropic, determine the flow area at the location where the Mach number is 0.9, and similarly solve for an ideal gas with K of 1.33. So what is given is, we know the gamma fluid is 1.4 and the area where the Mach number is 1.8 is 36 centimeter square. So we need to find out the area where the Mach number is 0.9. So for do that we'll use the area ratio using the throat area as the reference to find out the other area. So we'll take two conditions. So the flow is assumed to be isentropic, and since it's isentropic, you can assume that stagnation properties will remain same throughout. So the flow area at location where a Mach number is 0.9 can be determined assuming the throat reference. So first is we will take Mach number of 1.8. So from the table we will go to 1.8. The area ratio is 1.439. So that is given. So for 1.8, the area at that location where Mach number is 1.8 divided by the area of the throat section is 1.439. Next is we need to find out the Mach number at 0.9, the area ratio is, so for 0.9 the area ratio is 1.0089. so 1.0089 is the area ratio. So A2 is by area of throat is 1.0089. so since we know the area at Mach number of 1.8 is 36 centimeter square, we can find out the throat area. The throat area becomes 36 divided by 1.439, which comes out to be 25.02 centimeter square. This is the throat area. Next is, we know the area ratio between the area where Mach number is 0.9 divided by the throat area. So we can find out the area to be 1.0089 times the throat area. So it comes out to be 25.2 centimeter square. So that is the area where the Mach number is 0.9. Similarly, when we assume the gas to be ideal and with the gamma value of 1.33, so the area ratio is written as A by A star is 1 by Mach number into 2 by gamma plus 1 into 1 plus gamma minus 1 by 2 into Mach square raised to power gamma plus 1 divided by 2 into gamma minus 1. So for K of 1.33 and Mach number of 1.8, the area ratio, substituting the values, it comes out to be 1.4696. So here the same value can be used if the table is not provided. You can substitute K value as 1.4 and you will find out that the ratio comes out to be 1.439. So here we are substituting K as 1.33 and the area ratio comes out to be 1.4696 for the area at Mach number of 1.8 to the area of the throat, or where Mach number is 1. And there, from here we can find out the A star as 36 divided by 1.4696 comes out to be 24.5 centimeter square. And next is, similarly, we substitute Mach number of 0.9, the previous expression, and the area ratio A2 by A star comes out to be 1.0091. So from here we can find out A2 as 1.0091 into A star. So A star we have found out to be 24.5. So 1.009 into 24.5 gives out 24.7 centimeter square. The next question is, steam enters a converging nozzle at 5 megapascal and 400 degrees Celsius with a negligible velocity, and it exits at 3 megapascal. So we have a converging nozzle, so the inlet to the nozzle is at 5 megapascal and 400 degrees Celsius, and the exit is at 3 megapascal. So the inlet velocity is neglected. So for a nozzle area, exit area of 60 centimeter square, determine the exit velocity, mass flow rate, and exit Mach number if the nozzle A is isentropic and B has an efficiency of 94%. So we need to find out the nozzle exit area is given is 60 centimeter square. We need to find out the exit velocity, mass flow rate, and exit Mach number for cases, two cases. One, the nozzle being isentropic, and second, if the isentropic efficiency is 94%. So we'll see how to solve this. So the first is, the inlet stagnation properties in this case are identical to the inlet property. Since the inlet velocity is negligible, so we can assume H01 equals H1 because velocity is negligible. So we write H0 is H1 plus V square by 2G, V square by 2. So since velocity is negligible, we can neglect the kinetic energy and H0 becomes H1. So at inlet you have P which is equal to P0, which is 5 megapascal, and similarly H becomes H0, which is 3196.7 kilojoule per kg for P and T of 5 megapascal and 400 degrees Celsius. And similarly the entropy at this condition is 6.6483 kilojoule per kg Kelvin. So this value you are getting it from the steam table. Now at the exit we know the pressure is 3 megapascal. So since it's an isentropic nozzle, so your entropy will remain same, 6.6483 kilojoule per kg Kelvin. So using pressure and entropy, we get enthalpy as 3057 and the specific volume as 0.08601 meter cube per kg. So first is 5 megapascal and 400 degrees Celsius. So 5 megapascal and 400 degrees Celsius here. So you get 3195.6 in the table, here is 3196.7, and similarly entropy is 6.6458, and next is similarly you can take same 3 megapascal and the same entropy to find out the enthalpy at the exit and the specific volume. Now doing an energy balance across the nozzle, we get inlet enthalpy plus kinetic energy at the inlet equals exit enthalpy plus kinetic energy at the exit. Neglecting the potential energies, we get V1 is 0, so we get H2 minus H1 plus V2 square by 2 equals 0. So we can write V2 as root of 2 into H1 minus H2. So substituting the enthalpy values, so 2 into 3196.7 kilojoule per kg minus 3057 kilojoule per kg into 1000 to make it into joules. It comes out to be 528.5 meters per second. So now we can find out the mass flow rate. Mass flow rate is rho AV or AV by specific volume. So we know the exit area, which is given 60 centimeter square, so 60 into 10 power minus 4 multiplied by velocity which we have calculated, which is 528.5. So 528.5 divided by the specific volume, which is 0.08601 meter cube per kg. So it comes out to be 36.86 kg per second. So that is the mass flow rate through the nozzle. The next is we need to find out the Mach number. So what been asked is exit velocity which you have calculated, the mass flow rate, and then the Mach number. So to find out Mach number, so C is root of dou P by dou rho at constant S or entropy. So this we can find out with a finite difference. So root of delta P by delta rho, or rho can be written as 1 by specific volume, so delta 1 by specific volume. So for constant entropy value, which is S2 6.6483, we take since exit at 3 megapascal, we take it at 2.5 and 3.5 megapascal. So for this pressures and entropy value, my specific volumes are 0.09906 meter cube per kg and 0.07632 meter cube per kg. So substituting the values, so C is speed of sound is root of 3500 minus 2500 kilopascal divided by the specific volume is 1 by 0.07632 minus 1 by 0.09906 multiplied by 1000 to convert it into Pascal, so which comes out to be 576.6 meters per second. So now we can find out the Mach number, velocity by speed of sound. So velocity is 528.5 meters per second divided by the speed of sound is 576.6 meters per second. So it comes out to be 0.917. So next is when the nozzle is not isentropic, 100% efficient, but it is an efficiency of 94%. So here also the inlet stagnation property, is same as the inlet condition. So H0 is H1, so P1 and T1 same, so we will get the same enthalpy and entropy values at state 2. In the case when it is isentropic, so this is again the same value, but this is not the exit value, but assuming it as an isentropic process, 100% efficient. Now the nozzle efficiency is defined as H01 minus H2 by H01 by H2S is the isentropic value. So we get nozzle efficiency is 0.94. So H01 minus H2 divided by H01 minus H2S. So from here we can find out H2 be 3065.4 kilojoule per kg. So therefore we know the enthalpy, we know the pressure, which is 3 megapascal. So using this two we can find out the specific volume and entropy. So specific volume comes out to be from the steam table for 3 megapascal, go to 3 megapascal, and enthalpy of 3065 somewhere around 300 and 350 degrees Celsius. So get a specific volume as 0.08666 meter cube per kg and is entropy as 6.662 kilojoule per kg Kelvin. So now applying the energy balance steady flow energy equation across the nozzle, we get again H2 V2 is root of 2 H2 minus H1 minus H2. So substituting the values, we get velocity as 512.4 meters per second. So now we know specific volume, we know velocity, we can find out the mass flow rate. So mass flow rate comes out to be 35.47 kg per second. So if we see previously we got 36.86 kg per second. So having the efficiency dropped by 6%, your mass flow rate has reduced to 35.47 kg per second, close to 1.4 kg per second reduction. So again the velocity of sound for this case, we know the entropy at the exit, we will use that entropy and calculate C. So previously we used the inlet entropy, which is same as the exit entropy, but in this case it is not. So exit entropy 6.6622. So the same process, we take 2.5 megapascal and 3.5 megapascal for the finite differences. So this comes out to be C2 is 578.7 meters per second. So in previous case we got 576.6. So now we have got 578.7 meters per second. So the exit Mach number now becomes 0.885. Previously got 0.917. So with the nozzle efficiency reduced, Mach number is 0.885. So next question, we have steam entering a converging diverging nozzle at 1 megapascal and 500 degrees Celsius with a negligible velocity and a mass flow rate of 2.5 kg per second, and it exits at a pressure of 200 kilopascal. Assuming the flow through the nozzle to be isentropic, determine the exit area and the exit Mach number. So we are converging, diverging. We know the inlet conditions, which is 1 megapascal and 500 degrees Celsius, and velocity is integral. So these are your stagnation properties. In the mass flow, it is also given as 2.5 kg per second, and exit pressure is known. So we need to find out the nozzle area, exit area, and the exit Mach number. So to do that, first we know that the stagnation properties. So corresponding to that, the enthalpy values are, so stagnation pressure is 1 megapascal and stagnation temperature is 500 degrees Celsius. So your stagnation enthalpy is 3479 kilojoule per kg, and your entropy is 7.7642. So from the steam table, for 1 megapascal and 500 degrees Celsius, so that's what we get. Next is at the exit, assuming an isentropic nozzle, your stagnation pressure at the exit will also remain same, and what we know is exit pressure is known. So and since isentropic process, so exit entropy is same as the inlet entropy. So exit pressure is 200 kilopascal, so 0.2 megapascal, and entropy is 7.7642. So corresponding to this state point, our enthalpy is 3000 kilojoule per kg, and specific volume is 1.2325 meter cube per kg. So now applying an energy balance across the nozzle, we can find out the velocity. So velocity V2 is root of 2 h1 minus h2. So substituting the enthalpy values, I get velocity is 978.9 meter per second. So area, this is the exit velocity, so we need to find out the area at the exit. So since we know the mass flow rate, so mass flow rate is rho AB, or A into velocity divided by specific volume. So area will be mass into specific volume divided by your velocity. So mass is 2.5 kg per second, which is given, and your specific volume is 1.2325 meter cube per kg divided by 978.9 meter per second. So this gives you area of 31.5 centimeter square. So next is to find out the exit Mach number. Again the same process, we can find out the speed of sound. Speed of sound comes up to 563.2 meters per second. So the Mach number is 1.738. Excuse me. So the next question is, we have a convergent nozzle. The exit diameter is given as 2 centimeter, and the inlet flow is at 20 degrees Celsius and 101 kilopascal with other stagnation condition. So that is a stagnation property of temperature of 20 degrees Celsius and stagnation pressure of 101 kilopascal. So the nozzle has an isentropic efficiency of 95%, and the pressure drop is measured to 50 centimeter of water column. So find the mass flow rate assuming compressible adiabatic flow, and repeat calculation for incompressible flow. So first we'll convert the pressure drop from water column to kilopascal. So delta P is given as 50 centimeter of water column. So 50 into 9.8064. So it's rho GH density into G into height of the column. So it gives you delta P is 4.903 kilopascal, and since we know T0 is 20 degrees Celsius, so in terms of Kelvin it's 293.15 Kelvin, and P0 is 101 kilopascal, and since these are the stagnation property, we can assume inlet to be at velocity at 0. So the exit pressure is P0 minus delta P. So P0 is 101 and delta P is 4.903. So the exit pressure is 96.097 kilopascal. Since it's isentropic reversible adiabatic flow or isentropic flow, your stagnation property throughout the flow will remain same. So at the exit we can write it as using isentropic compression formula. So Te is T0 by Pe by P0 raised to power gamma minus 1 by gamma. So we can find out the exit temperature, which is 293.15 into pressure ratios divided by raised to power 0.2857, which gives you 289.01. So the exit velocity V square by 2 comes out to be Hi by He, which is Cp times Ti minus Te. So Cp is 1.004 times your temperature difference 293.15 minus 289.01. So V square by 2 is 4254.5 joule per kg. Since nozzle is 95% efficient, can be written as same velocity square by 2 divided by the isentropic case. So we have what we have calculated is the isentropic case. So nozzle efficiency, just like the previous one, we can write it as the enthalpy difference Hi minus He by Hi minus He when it is isentropic flow. So that is written in terms of kinetic energy here. So V square by 2 actual is nozzle efficiency time V square by 2 for an isentropic flow. So nozzle efficiency is 0.9 and the kinetic energy is 415.4.5, which gives you the actual kinetic energy change is 394.6.78. So with this, the actual velocity comes out to be 88.85, and in case of an adiabatic flow, the velocity comes out to be 91.15 meter per second. So now using this, your Te actual is Ti minus V actual square by 2 Cp. So T actual comes out to be 289.2 Kelvin, and similarly rho density actual is at the exit is Pe by RT. So exit pressure we have calculated 96.097. We know temperature 289.2 into R This comes out to be 1.158 kg per meter cube. So now we know the density, the area is known, nozzle exit diameter 2 centimeter, and velocity. So you can find out the mass flow rate. So rho AAV, so rho is 1.158, area is pi by 4 into 0.02 square, and velocity is 88.85 meters per second. So this comes out to be 0.0323 kg per second. So for incompressible flow, V square by 2 gives you Pi minus Pe into specific volume. It comes out to be Pi minus Pe into RT by P. So this is from the Bernoulli expression. So we get Pi minus Pe is 4.903 into R is 0.287 into temperature is 293.15 divided by 101 kilopascal. So this comes out to be 4084 joules per kg. So V square actual by 2 is nozzle efficiency into V square ES by 2. So nozzle efficiency is 0.95, and the isentropic flow case kinetic energy is 4084. So the actual one is 3880 joules per kg. So the actual velocity comes out to be 88.09 meters per second, and the mass flow rate comes out to be 1 by 0.833 is the density, density into area into velocity, which comes out to be 0.0332 kg per second. So it's predicting a higher mass flow rate compared to in case of incompressible flow. So next question is, we have steam at 800 kilopascal and 350 degrees Celsius, which flows through a convergent divergent nozzle that has a throat area of 350 millimeter square. The pressure at the exit plane is 150 kilopascal and the exit velocity is 800 meters per second. So the flow from the nozzle entrance to the throat is reversible and adiabatic. Determine the exit area of the nozzle, the overall nozzle efficiency, and the entropy generation in the process. So the inlet conditions are given at 800 kilopascal and 350 Celsius. It's flowing through a convergent divergent nozzle, and the throat area is given as 350 millimeter square, and the exit pressure is also given is 150 kilopascal, and the velocity is 800 meters per second. So we assume that flow is reversible and adiabatic, so isentropic flow. In entrance to the throat is isentropic. Determine the exit area of the nozzle, the overall nozzle efficiency, and entropy generation in the process. So first, the inlet stagnation properties. Inlet condition 3161.7 kilojoule per kg, and entropy 7.4089. Then your P star by P naught is 2 by gamma plus 1 raised to power gamma by gamma minus 1, which comes out to be 0.54099 for gamma of 1.4, for steam 1.12. Then P star is 432.7 kilopascal. And so at corresponding to 7.4089 and P star of 432.7 kilopascal, my enthalpy at throat is 2993 kilojoule per kg, and V star is 0.5687 meter cube per kg. So delta H is V square by 2. So V star is root of 2 into delta H, H1 minus H2. So velocity at the throat is 569.9 meters per second. So from this we can find out the mass flow rate. So mass flow rate is area into V divided by specific volume. So area is 350 mm square, so 350 into 10 power minus 6 into the velocity 569.9 divided by 0.5687. So mass flow rate comes out to be 0.3507 kg per second, and the exit enthalpy is H naught minus V square by 2. So we know the inlet enthalpy and exit velocity. So He comes out to be 2841.7 kg per second, kilojoule per kg. So at exit we know the exit pressure and enthalpy. So exit pressure is given as 150 kilopascal, and enthalpy is 2841.7 kilojoule per kg. So corresponding to this pressure and enthalpy, we can find out the specific volume. So from the steam table, for 190 kilopascal and 2841.7, the specific volume comes out to be 1.395 meter cube per kg, and the corresponding entropy is 7.576 kilojoule per kg Kelvin. So the exit area is now same, m dot is rho AV. So substituting the values, m dot is m dot into specific volume by exit velocity. So 0.3507, which we have found out the mass flow rate, into specific volume is 1.395 divided by velocity is 800. So it comes out to be 6.115 into 10 power minus 4 meter square. Say 6.1 centimeter square. So the entropy generated is nothing but the exit minus inlet entropy, is 7.576 minus 7.4089. So it comes out to be 0.167 kilojoule per kg Kelvin. So next question is steam flowing at 15 meters per second and 1800 kilopascal and 300 degrees Celsius. So this is 300 degrees Celsius. Expands to 1600 kilopascal in a converging nozzle. Find the exit velocity and area ratio, AE by A inlet. To what pressure should the steam expand to reach Mach 1? So we need to basically find out the critical area ratio to for it to reach Mach 1. So inlet state is for pressure of 1800 and 300 degrees Celsius. So inlet specific volume is 0.14021 meter cube per kg, and enthalpy is 3029.21 kilojoule per kg. Entropy 6.8226 kilojoule per kg Kelvin. So now exit pressure for the same entropy and the exit pressure of 1600 kilopascal. The specific volume is 0.15371 meter cube per kg, and the exit enthalpy is 3000.995 kilojoule per kg. So applying an energy equation, the exit velocity is inlet velocity square plus 2 into Hi minus He. So V is root of the inlet velocity is 15, so 15 square plus 2000 into your enthalpy difference, so comes out to be 238 meter per second. So the mass flow rate will be same across the nozzle. So area ratio is AE by AI is specific volume E by specific at exit divided by specific volume at the inlet into uh, velocity at the inlet by velocity at the exit. So we get 0.15371 divided by 0.14021 multiply by inlet velocity is 15, exit velocity is 238. So this comes out to be 0.069 is the area ratio. So for area ratio to be such that we get Mach number of 1 at the exit. So for gamma is 1.327, T exit by Ti is P by Pi raised to power gamma minus 1 by gamma. So exit temperature is 556.76 Kelvin. So exit velocity is so if you assume in gamma is constant 1.327, so exit temperature is 556.76 Kelvin and the exit velocity is 248 meters per second. So for this case the area ratio now will become in same formula we get V by Vi is Pi by P raised to power 1 by gamma. Substituting we get area ratio is 0.0661 if we assumed it to be an ideal gas. Next is we need to find out what pressure should the exit be for it to reach Mach number of 1. So these are the corresponding stagnation property when gamma is 1. So P is P naught by 1 plus gamma minus 1 by 2 into Mach square. So it comes out to be 974 kilopascal. So this is the pressure to which it has to be, the exit pressure should be for it to reach Mach number 1 at the exit. So next is we have a convergent divergent nozzle which has a throat area of 100 millimeter square and an exit area of 175 millimeter square. So the inlet flow is helium at stagnation pressure of 1 megapascal and then stagnation temperature of 375 Kelvin. What is the back pressure that will give sonic condition at the throat but subsonic everywhere else? So for this to occur, we have helium gamma is 1.667. So this is the throat section. So we have at the throat Mach is 1 but subsonic everywhere else. So that is the case. We have to solve. So that is you can see case C. Here it reaches Mach 1 and then it is subsonic everywhere else. So for first we'll assume the critical ratio to find out the pressure at the throat. So P star by P naught is 2 by gamma plus 1 raised to power gamma by gamma minus 1 and then the area ratio A by A star is given by 1 by Mach number divided by into 2 by gamma plus 1 into 1 plus gamma minus 1 by 2 into Mach number square raised to power whole raised to power gamma plus 1 by 2 into gamma minus 1. So using this we can find out the P star by P naught value is 0.4867 for gamma of 1.667. So P naught is given as 1 megapascal, so we can find out P star is 486.7 kilopascal, and then area ratio comes out to be 175 by 100, which is 1.75. Because the area is given, so 175 divided by 100 throat area, so 175 mm square divided by 100, so comes out to be 1.75. so now we know the area ratio, which is the left hand side. So here we know the gamma value, so only unknown is the Mach number, so we need to find out the Mach number. So substituting initially Mach number is 0.4, get area ratio is 1.56, which is lower than the value which we require. So reducing the Mach number by 0.3, we get area ratio is 1.9894, so this is somewhere in between. So again substituting Mach number of 0.35, so we get area ratio as 1.741, which is close to what we need. And then doing an interpolation, we can find out that Mach number at the exit should be 0.348. So now we can find out the exit pressure. For that, P naught by P is given as 1 plus gamma minus 1 by 2 into Mach number square raised to power gamma by gamma minus 1. So substituting the value and Mach number of 0.348, we get the pressure ratio to be 0.9058. So exit pressure ratio is 0.9058 times the stagnation pressure, which is 1 megapascal. So the exit pressure comes out to be 906 kilopascal. So if your exit pressure is 906 kilopascal, then the case C happens where you reach sonic velocity at the throat, but the flow remains subsonic everywhere else. So next question, the final question, we have a 1 meter cube insulated tank which is containing air at 1 megapascal and 560 Kelvin. So the tank is now discharged through a small convergent nozzle to the atmosphere at 100 kilopascal. So the nozzle has an exit area of 2 into 10 power minus 5 meter square or 0.2 centimeter square. So find the initial mass flow rate of the tank and find the mass flow rate when half the mass has been discharged. So first case we'll see the back pressure ratio. So outside pressure is 100 kilopascal and inside is 1000 kilopascal. So pressure ratio is 100 by 1000. So if you calculate the critical pressure ratio, P star by P naught using the 2 by gamma plus 1 value in this expression, we get critical pressure ratio, which is 0.5283. So the pressure ratio is lower than the critical pressure ratio. So the initial flow is choked with the maximum possible flow rate. So we get the exit Mach number to be 1. The pressure at the exit will be 0.5283 times 1000. So we get 528.3 kilopascal. So the exit temperature will be T star, so 0.833 into 560 is the exit pressure ratio. So this we can directly get it from the table also. So in 460.7, so exit velocity is root of gamma RT because it's a sonic velocity. So gamma is 1.4, R is 1000 into 0.287 into 466.7. So exit velocity comes out to be 433 meters per second. So exit specific volume is RT by P. So R is 0.287 into 466.7 divided by 528.3 kilopascal. So this comes out to be 0.2535 meter cube per kg. So the mass flow rate comes out to be area into velocity divided by specific volume. So area is 2 into 10 power minus 5 and velocity is 433 divided by specific volume 0.2535. So this comes out to be 0.0342 kg per second. So the initial mass flow rate, initial mass in the tank is P1 V1 by RT1. So initial pressure is 1 megapascal, so 1000 kilopascal into volume is 1 meter cube divided by R is 0.287 and temperature is 560. So this comes out to be 6.222 kg. So the mass at state 2 is 50% of the initial mass. So the mass now in the tank is 3.111 kg. So assuming an adiabatic reversible expansion, we get V2 equals P1 into V1 by V2 raised to power gamma. So V1 by V2 is 0.5 raised to power 1.4. So we get P2 is 378.9 kilopascal, and similarly T2 we get 424 Kelvin. So the pressure ratio is still less than the critical and the flow will remain choked. If you see P is 100 by 378.9, which is 0.264, which is less than 0.5283, so it will still remain choked. So the exit pressure now will be 200.2 kilopascal and the exit temperature is 353.7 and the exit velocity is 377 meters per second. It has reduced from previous. So the mass flow rate now is again AV by P by RT. So area is remain same, 2 into 10 power minus 5. The velocity is 377 and then pressure 200.2 divided by R value into temperature is 353.27. So the mass flow rate now drops to 0.0149 kg per second. So with that I finished today's problems on compressible flow. So tomorrow we'll have a review session on the topics covered in the applied thermodynamics course, and that will end the problem solving sessions. And thank you. So with that I'll end the session. Thank you.